Today's episode is an interview with Dr. Brent Mom, who has a PhD in muscle biology and is currently a postdoctoral fellow studying the molecular mechanisms that contribute to muscle function. Really cool stuff. During the episode, we discuss the importance of muscle for health and longevity, mechanisms that contribute to the loss of muscle function as we age, as well as how we can use research to inform us on new interventions and therapies to improve health related outcomes in the general population. I'm sure you guys will find this episode extremely informative and interesting. I hope you enjoy the episode. What's up, Brent? How are you doing, my man?
Good. How are you?
Doing great. Thanks for being here today. How about we kick things off by you telling us a little bit about who you are and what you do?
Sure. My name is Brent, and I am currently a postdoctoral fellow at the University of Massachusetts, working in the muscle biology laboratory. I am also a one-on-one nutrition and training coach. I've been doing that for the better part of the last 3 to 4 years now. Getting to that point in time, I had quite the journey growing up, going from dealing with my own little weight loss journey as a teenager and then trying to figure out how to go from that and learn how to understand scientific concepts and to try and apply those then to myself and how to help apply those to clients as well. So I went through an undergraduate degree in kinesiology, felt like I didn't know enough, I had to know more. And then I went on into a master's degree in exercise physiology, which kind of bit the bug for research. I wanted to get my hands directly in what's going to help impact people, yes, now with coaching, but also in the future with hopefully some research that might help inform whether it be disease prevention or disease treatment in the future, or whether to be the general public today. So that's what led me into going into a PhD in specifically muscle biology, looking at muscle structure and function, health and disease.
Cool, man. Just out of personal curiosity, did you get the undergrad in kinesiology because you wanted to get jacked like a bodybuilder?
So, kind of yes
Yeah.
and no. My initial thought of going into getting a kinesiology degree was I want to open a gym.
Okay.
That was my path. I was like, yes, I'm going to get jacked, but I'm going to open a gym. And then like 2 years in, I was like, I would hate to own a gym. That would be
Yeah.
terrible. I was like, well, what the heck do I do now? And that's when I took both anatomy and physiology, and then I took exercise physiology, and that's what really bit the bug. For was like, yeah, I want to know more about how this works.
Yeah. Isn't it so funny, man? Like we go into these degrees for undergrad thinking it's good for one thing and it's actually like not good for that thing at all. It's like if you actually want to be a gym owner, kinesiology is not the route you should go down. Just probably be like a business major or something. Um,
Well, the funny part about that is I had a business minor. I was actually going to do a double major in business and kinesiology,
okay.
but I just dropped down to a business minor. And I dropped the business minor because I went into a business law class and I failed it. Like every single test. The professor was like, people do awful on the first test, but every subsequent test after that, they tend to do better. The first test I got like a D, and then the second test I failed. And like I was like, I'm not getting better at this. I
Oh
can't do it.
man, that's rough. Well, at least you know what you're good at.
Right.
Yeah. Awesome, man. Well, how about you tell us a little bit about the importance of skeletal muscle, why it's important to study it, and what its role is in health and aging and disease prevention as well.
Sure. So this is one of the main aspects that the lab I currently work and focuses on is human skeletal muscle in healthy populations and then diseased populations. And I'll talk a little bit about that, what that means in a little bit. But the main purpose is that your muscle, whether it to be, so a lot of people look at it as like muscle size, but we like to primarily look at it as muscle function, which I'll define in a second, is radically important for you to be able to get up and have a good uh, quality of life, so to speak. The things you do every day, which we consider in the lab as activities of daily living, being able to go around a walk around the house, go pick up your mail from the the mailbox, being able to get in and out of your car. Those things are what are considered activities of daily living. And being able to complete those takes some amount of adequate muscle function, but it also takes an adequate amount of muscle mass to do. So there's two primary distinctions there, in that in the say the bodybuilding world or the gym world, we think of muscle size as like the primary determinant of, I want to have a bigger muscle. Bigger muscles mean more strength. If you look at many powerlifters out there, you'll see that those in the heavier weight classes tend to be those who are stronger. Now, this isn't a one-to-one relationship, though. Let's say if you put on 1 pound of muscle, you're not going to add 5 pounds to your bench press every single time you do that. There's a limit to how far that's going to go, and that's where the function component comes in. Is that you might be able to grow an obscene amount of muscle mass, but that's not always going to translate into an obscene amount of strength. So when we think of muscle function, essentially that is, you can quantify that based upon uh, strength per muscle size. So if you took, say, and people tend to do this like with the Wilks score, is that they take your total amount of weight you can lift and divide that by your body mass, or by how much you weigh. It's similar to what we do here, is that we look at how big a muscle is, we look at how much force that muscle can produce, and then we divide that force divided by the size, and that tells you in essence how strong that muscle is for a size. And that way, when we look at several different people, say we look at somebody who is uh, healthy, walking around, young, we can compare their muscle to somebody who is much older, or who is might be have some sort of disease, or have some sort of state where their muscle function is impaired. So that way we can compare across populations instead of having to just compare across, well, yes, I am young and healthy, I have a large muscle. Oh, well, the older population, the disease population has a much smaller muscle, and that's the primary determinant of their function. We can then look at the quality, quote unquote, of their muscle by normalizing it to strength, or strength divided by how big their muscles essentially are.
Yeah, cool stuff there, man. A quick question, because you're talking about obviously strength and size are related. It's not linear, right? We all know people who have perhaps bigger muscles and aren't necessarily stronger, and vice versa as well. Correct me if I'm wrong here, but strength isn't even necessarily just a byproduct of muscle itself, but it's influenced by the neuromuscular relationship, right? How efficient the nervous system is at activating particular muscle fibers. The anatomy is also important, right? Like origin and insertion, all of those things can influence how strong a muscle is in a particular person.
Sure. Yes. And that's also very appropriate. And it kind of need to take a step back and try to answer what actually causes muscle to contract. So there's several different systems, and you named a couple of them. Number one is the brain has to send a signal down to the muscle to say, hey, you've got to be contracting right now. We don't obviously think about this all the time. Like, you're not walking outside and thinking, I have to contract my quad, I have to contract my hamstring, and vice versa. It's an automated process that we don't have conscious thought over, unless we're going to lift weights in the gym, where you're saying, I need to push up this bench. So essentially, your brain sends a signal down your spinal cord out to the peripheral muscles that you want to be activating. And then at that point in time, there's a junction between the nervous system and the muscle to send a signal. And that signal tells the muscle you need to contract. So before we even get to the whole contraction process, that nerve conduction system, or the process of sending it from your brain down to your spinal cord, down to your muscles, that can improve. And it's one of the big reasons why you see substantial improvements in strength over the course of 1, 2, 3, 4 weeks of doing some sort of exercise program, is because those programs just get better. We get better at sending the signals. We send them a in pathways that are faster and that are stronger. so we can make the signal more amplified, essentially. And then the other side of the equation is, so that's the nervous side, is the muscular side, because it's the neuromuscular system. So the muscle side of the equation is essentially when you get that signal to the muscle, what does the muscle do with that signal? So essentially what will happen is you will have um, a couple different proteins that end up uh, interacting to essentially establish a connection. And how do I frame this? Um, Go through the mechanism. I'll talk about a little bit of history of where this kind of came from. But essentially, you have the neuromuscular junction, you have activation of the skeletal muscle, and that skeletal muscle, the end result is two proteins interacting and then producing force. They essentially interact together. It's called myosin and actin interactions. They interact, they go through what's called a power stroke. And that power stroke is the end result, which is causing the muscle contraction. So we tend to think of it as we have this whole muscle and we can shorten the entire muscle, but it's essentially billions upon billions of tiny little proteins interacting together. And then they go through a power stroke to then you see that entire muscle starting to contract down. Now, why this is important is that there's a lot of early theories of why muscle contracts. Like this wasn't something that just happened yesterday. We didn't 10 years ago wake up and we were like, how the heck does a muscle produce force? How does a muscle go through contractile velocities? There was theories well before the common era, 300 BC, where people just thought that animal spirits were being carried to muscles. Like you just had spirits from your brain that were just saying, hey, you should be contracting so you can go through this movement. And even Rene Descartes in the 1600s and in the 1800s with a couple of other individuals, they were suggesting that muscle worked kind of like rubber, and that it was kind of like this very pliable rubber-like material. But in the 1900s, we really made a lot of leaps and bounds forward with technology, started to understand what is happening not in the nervous system, but essentially what's happening in the skeletal muscle itself. It's with some different theories of muscle contraction. So what's really interesting is that there are two researchers, Hugh and Andrew Huxley, who have no relationship to each other and were in different countries back in the 1950s, who developed what is called the sliding filament theory. And they published on this theory back in Nature in 1954, the same year, the exact same issue and volume. Just so happens that they were doing two different experiments that came to the exact same conclusion at the exact same time about how muscle works. They just did it by two different methods. So essentially, they were able to, in the 1950s, image the smallest unit or the smallest functional unit of the muscle cell, which is called the sarcomere. And the sarcomere has two primary proteins or filaments that are associated with muscle contraction. And I mentioned them earlier, but they are the actin filament, which is a filament that looks kind of like uh, what's one of my professors used this at one time. It's almost like a strand of pearls put together. And then you have the myosin thick filament. So you have an actin thin filament that's here, and you have a myosin thick filament. And the myosin comes up, it binds to actin and goes through a power stroke, which eventually displaces the actin. And what you'll see, what these researchers noted, is that when contraction occurs, these filaments slide over each other, and that causes that sarcomere to shorten. And that's essentially what's happening at the whole muscle level too, is you have billions of sarcomere shortening, which is then causing the entire muscle to shorten. Now, the reason why all this background is important is because it directly helps us as researchers and as practitioners, hopefully down the road, understand how to target potential issues with disease states or with aging. Because the primary effectors of muscle contraction, the things that are causing force to be produced, the things that are causing whole muscle power production, is these proteins. So if we can alter these proteins in some way, or if they are being altered with disease or aging, we can then say, what targets do we want to specifically impact to improve function, to improve muscle mass from a size perspective, and then help out those populations.
Yeah, that's cool stuff, man. Here's an interesting question. Do we know So I think one thing that we probably should have touched on a little bit more earlier, because we talked about um, the importance of muscle and all this, is why is this so important? Why is muscle so important as we age? Right. And I think it's a pretty simple question, but can you address that question before I ask my follow-up question, which is directly around everything that you're mentioning now? Why is muscle so important as we age? How can muscle help prevent the or prevent the development of particular diseases? Let's talk about that for a little bit.
Sure, sure. So the first thing that comes to mind is that it's been well established that there is a lower limit to the amount of muscle mass that we have, and that correlates to essentially our mortality or our
Yeah.
risk of dying. So once we get to a certain point, which in the research is termed frailty, or just a loss of total muscle mass and muscle function, our odds of dying or our risk of dying is substantially increased. And so in the next, 1 to 5 years, our chances of dying are rather high because we have no skeletal muscle mass essentially. So that's one end of the spectrum, and that's been well established in disease states as well. So whereas muscle mass or muscle function correlates highly with predictability of dying or our mortality. So the other question is, well, why might that be? Number one is we just essentially can't take care of ourselves. We don't have the ability to get up and prepare food. We don't have the ability to get up and do things like, use the bathroom. We don't have the ability to essentially get out of bed. And if you are in bed for a substantial portion of your life,
Yeah.
your lifespan is going to shorten substantially. The other thing that you asked is about how can having muscle mass or muscle function improve our general health and well-being. There's two specific ways that come into mind. Number one is something that a lot of people think about, specifically if they have heard of the term diabetes before, is that a muscle works as a almost a modulator of metabolic health, so to speak,
Yeah.
in that if you go through muscle contractions, it actually helps uptake different things. Like it helps to uptake proteins into your muscle cells to facilitate rebuilding. It helps to uptake glucose into your cells to help manage blood sugar levels. The second one, I am now blanking on it. It'll come back to me in a second.
That's all good, man. I talk about this so much too because people don't understand how important muscle is for health. It's like can help you prevent diabetes, cardiovascular disease, even age-related cognitive decline. I'm sure a big part of that is, with resistance training, the amount of mental focus that's required there, even can reduce the risk of specific types of cancers. And people tend to maybe using the term people is a big generalization, but a lot of individuals who don't resistance train and I'm just like, oh, I don't care about looking like I'm muscular. It's like that's not the point, right? I mean, it's
Yeah.
it's cool, it's an aspect of it, but as we age, it becomes incredibly more important for our health. Now, the follow up question that I wanted to ask is, um, you mentioned that there are different factors that influence muscle function, right? The nervous system is an aspect of it. The way the contractile proteins work are an aspect of it. I'm sure there are a number of other mechanisms. And we also know that as we age, in general, people lose muscle mass and they lose muscle function. Do we know and I'm sure the answer is different depending on the particular disease, but what the primary contributor is to that? Why do we lose muscle? Is it more because we have losses in this neuromuscular connection or the efficiency of our nervous system? Talk a little bit on that.
But before I say that, you make me think of something is that it's weirdly enough, we always think of it as we're younger as, or when we're younger, we always essentially train like our life depends on it. If you're really into fitness, like you get in the gym, you go after it, and you're just
You
on
almost
top of
die
it. Or
every day.
you almost die every day. You're crawling out of the gym. And the funny thing is, the people who actually need to be training like their life depends on it are older adults. They're the
Yeah.
ones who probably should be going to the gym and hitting it really hard, versus us younger individuals probably don't need to push nearly as hard.
Yeah.
Um, so some factors that might impact muscle function and size as we age. It's kind of multifactorial. There's both uh, alterations or adaptations that happen to the nervous system, and to skeletal muscle. The nervous system, what tends to happen with aging, and bear in mind this is in association with becoming more sedentary. People who go from being more active when they're younger to less active when we age. So in those circumstances, it's hard to discern between aging and inactivity. But we try and do our best to understand at least what's happening with the both of those as the aging process happens. And from the nervous system perspective, we have changes to motor neurons. So the neurons that are coming from the spinal cord that go down to the muscle cells themselves, they may actually start to de-innervate from muscle cells. They might retract from those muscle cells, and then other nerves around there will try and come in and re-innervate those same muscle cells that were de-innervated, so that they can start contracting again. So that's something that tends to happen in older individuals. I believe it tends to happen more so between like ages like 75, 80, 85. So a little bit up there in age. But that's one mechanism as why muscle function may change. And a big key factor in that is that they tend to, so far as I understand, move towards more slow contracting muscle fibers. And I'll explain more in a second why that matters. But that's one factor. A second factor that's going to impact muscle function is what a lot of people in the fitness community are concerned about, which is protein synthesis. So, protein synthesis is essentially where you have proteins either being added to the system, being churned, or being foods that you intake that are proteins. They get broken down and they get incorporated into your muscle tissues or other peripheral tissues in your body. So they can get added or they can get subtracted. So the subtraction is the degradation, the added is the synthesis portion. And if you have a imbalance between those two, such that degradation is higher than the synthesis, you will have a slow degradation of your muscle cells. They will become smaller, you might lose some, and your overall muscle size will decrease. Now, this comes to the added part of if you have poor or an inadequate balance between those two, between protein synthesis and protein breakdown. It's not only thinking about those myosin and actin I talked about earlier. So the myosin and actin proteins that bind together and go through the power stroke to create force production, there are other proteins in our muscle cells. And those proteins can directly alter the contractile qualities or contractile function. So what can happen is you might have a what's called a post-translational modification. This is getting a little bit more technical, but you essentially have something added to the protein. So you've got this myosin protein that's kind of hanging around, and you've got some sort of alteration to that myosin protein by it can be phosphorylated, it can be acetylated, it can be carbonylated. There's a bunch of different things that can be attached to this protein, but essentially changes the function of that protein. So if you have an alteration in protein synthesis or of the protein turnover occurring, and some of these proteins are hanging around for a long time, there's going to be these random, maybe not random, but different groups added to the proteins that cause the function to change. And this is really important, particularly in aging populations where you have a slowing of that protein turnover. You have myosin and actin that have not been refreshed or renewed for a long time. And you have a post transitional modification that comes in that alters the way those proteins function. So essentially, what this can do is if you have a protein that gets carbonylated or a protein gets phosphorylated, it might slow down how fast the myosin and actin interact. So, from a one single protein perspective, if you took one myosin protein and an actin filament and just had them bind together, yeah, it slows down. They don't interact as fast and they might stay bound together longer. But what does that do to the whole muscle? So if you scale this up from single proteins to a whole muscle fiber to an entire muscle, if you have billions upon billions of myosin and actin interactions that are now happening slower, we get into an issue of the contractile velocity of that muscle, or essentially you can think of it as how fast you could potentially curl your bicep is going to slow down. Now, it might not seem like a small amount of slowing is going to have a substantial impact, but your ability to stop yourself from falling, let's say you trip and you need to put your leg out in front of you. Let's say you trip and have to grab onto something so you don't fall over. The ability to do that when you're aging or if you're in a disease state is going to be much less if your myosin active proteins aren't interacting as fast. So that's another big impact or variable that's going to essentially impact muscle function with aging that can change. And it particularly happens, and we can talk about this in a little bit, due to changes in hormonal status of individuals.
Yeah, dude, that's a lot of really cool stuff. I'm sure that's also what you were just mentioning. One of the main reasons why in sports we see, or in physical performance overall, we see a loss of speed and power a lot earlier than we do maximal strength, right? Because we know that to move the heaviest weight possible, you're going to be moving slowly anyways. So perhaps maximal strength isn't impacted as much. And then even anecdotally, you see sports like gymnastics, which are very speed and power focused. The best athletes are a lot younger than perhaps the best power lifters, where there are people in their 40s still continuously getting stronger.
Yeah, yeah.
It's cool to see how the physiology translates to real life performance in sport. What is some of the work that you are currently working on in your lab, and what's the overall mission or goal of the work that you guys are doing in your lab?
Sure. So our lab is actually rather unique compared to most. We study skeletal muscle function, and we also do some of this in cardiac tissue as well, but primarily skeletal muscle function. We study it from molecules up to movement, essentially. So we try and relate what's happening at the molecular level. So between those myosin and actin level interactions. We scale that up to the cell. We then scale that up to whole muscle function. So you can think of when I say whole muscle function, if you stuck yourself in a leg extension machine and we're doing some leg extensions, we have a very fancy machine called a Biodex that lets us control a bunch of different variables. It looks exactly like a leg extension machine, but we could correlate those myosin actin interactions up to that level. And then we think of then physical function, physical performance. And when I say that, I'm thinking of how fast you can walk 6 meters, how many times you can stand out of a chair, how long it takes you to get from sitting to standing, and some of those physical function performance like that. So that's one of the main reasons why our lab is unique is we do our experiments on multiple anatomical levels to say what can we change at the molecular level to then impact physical function. And it's not necessarily saying, okay, well, we have all these changes happening with molecules. Well, then why the heck does that matter? Because if you can't say that this one change that we are making or these things that we're doing in the lab is impacting physical function, then what is the purpose of your research at that point in time outside of generating mechanisms or mechanisms for understanding or hypothesizing why things may change? So that essentially allows us to take the experiments that we do and apply them to different populations or different, aging or disease states. So what we do then is we study what we have studied in the past, participants with heart or people with heart disease. Again, those in aging states are, comparing, say, ages 30 to 40 up to 65 to 75. Chronic kidney disease, that's a big topic that I've been working on. Um, People who have cancer, people who are obese, people who are experiencing just muscle disuse. So you can think of people who either uh, an interesting muscle disease case is just going up into space and spending time in space because that's unloaded, unweighted, as well as we are branching out into muscle fatigue. So, what we are able to do with these is we may take a population, for example, chronic kidney, or well, let's start with heart disease. So, if you take a muscle biopsy from heart disease, people who have heart disease, we test them, or we test their skeletal muscle. We pull single fibers from a bundle of muscle fibers. So you've got a chunk of muscle tissue. We pull a single fiber, a single cell, and we attach that single cell to a force gauge and a length motor. And we essentially can dunk this cell into different solutions to make it contract. And when we make it contract, we can test essentially the properties of the myosin and actin, how they interact, how quickly they interact, how many of them are interacting together to produce force. And then we can also understand how fast they contract. So we can essentially make them shorten as fast as they possibly can. And then by those two metrics, by how much force they produce, how fast they contract, we can then understand how much power they produce. So that gets from the molecular to the cellular, and then up to the whole muscle, like I mentioned earlier, and up to the physical function. So if we look at like participants with heart disease and how this might impact them, you might be thinking, well, my heart, why the heck does that matter for my muscles? Like the heart itself is a muscle, but why does that matter for my quadriceps? Why does that matter for my biceps? Well, that's a question that many people had not thought of outside of we see a decrease in muscle mass as the disease progresses. And this goes with most diseases: cancer, kidney disease, diabetes, heart disease. We see a decrease in muscle size. So most people focused on it's a muscle size issue. People's physical function declines as the disease progresses because they lose muscle size. Now, yes, that is a factor in it, but it might not be the only factor. And the way to determine this is if you take, especially in our circumstance, if you take a biopsy from an individual, you take those single muscle cells and you test them, and you test how much force they produce. They actually, when you normalize again to that muscle size, they produce less force. So if you have a muscle from a healthy participant, a muscle fiber from a healthy participant, and a muscle fiber from a disease participant with heart disease, if those cells are the same size, the exact same size, the one with heart disease produces less force.
Mm.
And when we drop down to the molecular level, that change in force tends to be due to, number one, there's less interactions occurring, so less myosin actin are binding. Number two is because the rate at which they interact, so how fast they bind together and how long they stay bound together, also drops down. So that's actually tends to be a hallmark of what we see in chronic disease states, or at least to what we've studied up to this point, is that in heart disease, in chronic kidney disease, in populations with certain specific types of cancer, and in some circumstances with aging, particularly in females, there is a slowing of these rates, a slowing of how fast myosin actin bind, and then how fast they unbind from each other. So the question is, we have all of these experiments. We have all these experiments that can essentially tell us what's happening to the muscle. But what do we do with that? And that's where we can start to intervene, essentially. And that's why understanding the structure and function of skeletal muscle is important, is because we can start to say, we know that these proteins are interacting slower. What types of exercise can we do that might improve that? So is it that we just want everyone doing 3 sets of 10 of squats every single, Monday, Wednesday, Friday? Or do we want them doing something more specific? Like in the world of research, power training is not powerlifting. Power training is essentially doing very high speed contractions with no weight, versus many people may think of powerlifting as I'm trying to lift as much weight as I possibly can. So if you were trying to speed up the interactions between these proteins, you might say, okay, let's do something that is specific to that. And the contractions specific to that are going to be ones that are very high speed and that may be very low load. So now we can start to target essentially the adaptations that we want to see.
Hey guys, some of you may not know that I'm the scientific advisor for a supplement company called Outwork Nutrition. I help with the formulation of new products to help ensure that they're effective and backed by science. Unlike many other supplement companies out there, we don't rely on exaggerated claims or flashy marketing tactics. Instead, we let the science speak for itself. We take pride in formulating products that deliver real results, helping you achieve your fitness goals in a meaningful way. If you're in the market for supplements like protein powder, pre-workout, or recovery products, make sure to check us out at outworknutrition.com. And as a thank you for being an avid listener of this podcast, use code Joey for an exclusive discount at checkout. You can find the link to our website down in the description of this podcast episode. Remember, our goal is to empower you with science-backed supplements that truly make a difference. Choose Outwork Nutrition and elevate your fitness to new heights. Yeah, it's really cool, man. So it sounds like based off some of the stuff that you're saying, yes, muscle size, loss of muscle size is a factor that contributes to disease progression, but maybe it's not the primary factor, right? It's maybe some of these underlying mechanisms that we see in the cellular structure of muscle that are also causing a loss of muscle mass. But perhaps these are more of the primary drivers, for lack of a better term, for the progression of disease, like lack of power, right?
Mhm. Yeah, it's hard to dissociate the two
Yeah, yeah,
because there it's interesting because there's a lot of labs out there that will either focus on structure or that will focus on function.
yeah,
And the funny part about it is if you dive down into the molecular level, like people who do single molecule experiments, um, those two they butt heads all the time. They're like someone's like the structure shows us this, and the function guys are like, oh, but the function shows us this, and they have this ever never ending debate on who's right about how these proteins work. But the reality is, the structure determines the function.
yeah,
And if you need a certain type of function, that's going to determine how the protein has to be structured or how the muscle has to be structured. And so that means if you want to produce more force, then you probably will at some point have to have a bigger muscle. And that bigger muscle needs to have more primarily myosin and actin. But if you have just a bigger muscle, that's not always necessarily saying that you're going to have more myosin and actin binding.
yeah,
A primary, an interesting note on this is that there have been models of what's called myostatin inhibition, which essentially myostatin is a regulator of total muscle mass. And say if you increase your myostatin, the myostatin expression gene, you will have a loss of muscle mass. So let's say, oh, let's just get rid of the myostatin and inhibit it completely. Well, you can do that in mouse models. You can do that in rat models. What happens is they become gigantic. They're like the hulks of mice, and they look awesome, but their function is terrible. So their grip strength is the same or less than their counterparts who don't have um, uh, that inhibition of the myostatin gene. So it's not necessarily to say the muscle size is the only factor. It's how that muscle is structured and organized. What's very interesting is that in some different disease populations, specifically chronic kidney disease, is that when you look at the structure of their muscle, like we've seen in our lab that the muscle fibers, the single cells from mice with chronic kidney disease, are actually bigger than the muscle fibers from the control mice, the healthy mice. The fibers actually get bigger. But if you look at the structure, the ultra structure of the fibers, so like how they're organized down to the molecular level, what you see is that with the disease, they end up looking like, for lack of a better term, they look trashed. It's almost like you put this single fiber or you put this mouse through like the worst exercise program or the most intense exercise program on the planet, and their muscle fiber looks destroyed.
Mhm.
So if you have a muscle fiber that looks completely disarranged and disarray, it's not going to contract very well. Even if you have a lot of size, it doesn't really matter how much size you have if you can't produce enough force to be able to, again, get out of the chair, walk down the street, or do some of those activities of daily living.
Yeah, that's super interesting, man. What you were mentioning earlier in terms of muscle fibers from an older versus a younger individual, if you control for size, the muscle fiber of the older individual still seems to produce less power, less force. Is that a finding from your lab specifically?
Yeah. So, and I'll quantify, I'll qualify this a little bit more because that's not always the case. In that there is a sex-based difference here, in
Okay.
that it's not uncommon. It's not uncommon to see that, and this was a published paper back in 2013, well before I joined the lab. Some of my advisors' work showing that male participants, they might see a decline in, we call it specific tension. What specific tension is, it's force normalized to size, or
Yeah.
force accounting for the size of the single fiber. But that force production declines in males
Okay.
with age. In females, it doesn't.
Mm,
It actually goes up. So we
interesting.
actually see that the force increases with age in females. Now you might be like, well, then why does this even matter? Why do we care about this? It's because we're not only concerned about the force, we're concerned about how fast these muscles contract. Because, like you stated earlier, especially speaking of like power and sprint athletes, people who need to focus on very explosive movements, the contractile velocity is one of the big determining factors of power production. Force production, or overall strength of a muscle fiber, has a relatively smaller impact to power production than contractile velocities do. So what happens with older females, and this happens to males as well to a certain extent, is we see a slowing of the interactions between the myosin actin. So they slow when they bind, and they stay bound together longer. So the reason why they produce more force is because the proteins stay bound together longer. If
Mm,
you have more proteins that are bound together longer, they're going to be stiffer and produce more force. But that comes at the expense of slower contractile velocities. So the contractile velocities aren't nearly as fast for older females. We're hypothesizing that. We're doing studies at the moment to essentially say that's happening. But we see that at the whole muscle level. So when you put someone in a dynamometer, what I called the leg extension earlier, the Biodex machine, we see that um, maximum contractile velocities are slowed, especially in older females. And that's essentially what we're seeing at the molecular level. And that's why it's a big determining factor as to why strength is not the only uh, it's not the only correlate looking to whole muscle function, because sometimes we see it go in the opposite direction that we might assume. We might see that with age it actually increases, but whole muscle function declines because the contractile velocities slow down so much
mm.
more.
That's cool stuff, man. Are there any other I just want to know what other cool stuff you guys have found in your lab, because this is all really interesting. I mean, a lot of this stuff is information that I have some base knowledge about, but definitely had no idea about sex differences or differences in uh, power production as we age versus force production. What other cool findings have you guys seen, and what are, you just touched on it a little bit, but what are some of the things that you're working on to hopefully find in the future?
Sure. So we again, this is one unique perspective of our lab, is that we do a lot of different, or we study a lot of different populations. So my advisor's primary interest is aging populations and resistance training, or some sort of exercise intervention to help promote improvements in skeletal muscle function. So that we have a study wrapping up currently that's looking at I guess the power training, or fast contraction, low load, versus resistance training, high load, slow contraction velocities, in both males and females who are older adults, so ages 65 or 75. That has been the primary focus of the lab for the better part of the last 6 or 7 years now. COVID kind of extended that a little bit. Um, the other primary focuses of our lab, so that's the human focus. We have another human study currently ongoing at the moment, looking at fatigue in older adults. So essentially, we have three different groups. We have younger participants, we have older participants, and then older participants who are mobility impaired. So people who have difficulty moving around. And we want to understand what might be the cause of older adults experiencing more muscle fatigue as we age. So compared to younger adults, what causes older adults to have more muscle fatigue? So what we do there is we essentially manipulate the solutions we use to simulate fatigue. And when I say fatigue, it's not just saying like I don't feel like getting up out of the chair. It's essentially saying that we have metabolic byproducts that build up in our muscles that cause our muscles to produce less force. So we can artificially manipulate that in the solution to drop force production and then understand how the myosin and actin molecules are interacting together. And then we can pull back and look at the different populations we're studying and to see if those interactions change between younger adults, older adults, and the mobility impaired older adults. So that's a study that's ongoing that I currently have my hands in for my postdoctoral work. Some other interesting things that people may find maybe a little more interesting to maybe sports performance of that sort is several years ago, we undertook some experiments looking at male mice who had been supplemented with two different things. Number one, flutamide, which is a uh, or an androgen receptor antagonist. So something that blocks the impact of testosterone on muscle. And then we had another group of mice that was supplemented with estrogen, and to understand essentially what was happening to their skeletal muscle function when you give male mice estrogen. So this is a very short term or short duration and low dose of both of these. It was 2 weeks of exposure at a dose that would be for estrogen borderline physiologic for a female or something of the sort. And then for the uh, androgen receptor blocker, that essentially just was a low enough dose that would be used for, say, prostate cancer patients. So the reason why this study was important is not necessarily because we're looking to say what's happening when male mice are or when males like transition to being female. It was mostly to look at, what happens in states of prostate cancer where you might see diminished testosterone levels, what happens when you see people who are obese who might have higher levels of estrogen and lower levels of testosterone. And again, it is a secondary ancillary question that we had: what might happen when you increase the level of estrogen in males, and what is the ultimate factor or determining factor of potentially changes in muscle function? So, what's very interesting about this work is, and many people may find part of this surprising, part of it not surprising, is that when you block the action of testosterone, you see a reduction in force production. And that's across, slow contracting, fast contracting, and really fast contracting muscle fibers. Force production drops. Contractile velocities, we're predicting based upon our experiments that they also slow down. So we see a reduction in force, reduction in potential contractile velocities. And then the thing that people may find a little more interesting and maybe not as, or a little more surprising, is that the estrogen, number one, it did not reduce force production in muscle fibers that humans express. The second thing is that in muscle fibers that humans do express, especially ones that people associate with sports performance, which are some faster contracting fibers, the kinetics, or essentially how fast these proteins bind together, they got faster, which essentially is saying that the contractile velocities may get faster when you increase the level of estrogen in these males' bodies. Be in mind, we have to take this in the context of the population study. It's a mouse model, it's a short duration, and it's a low dose of estrogen. However, there are preliminary findings that I'm currently working on writing up where we have taken longer durations of 8 weeks and higher doses of estrogen and seen the same thing, where we have a quickening of those kinetics, or a quickening or a faster shortening of the single muscle fibers, or faster contractile velocities. And we don't see diminished levels of force production. So many people, are a little bit on edge about how sports performance may be altered by changing or by the how do I term this? By more people being willing to accept gender transitions and things of the sort and how to incorporate it into sport. And it's going to be interesting how research shows how muscle function is changed by altering these hormonal levels in the body, which clearly with age they do. Clearly, with age and menopause and changes in testosterone, changes in estrogen, there is a change to muscle function. And now, if we look at younger populations, clearly, if we, give men, if we give them testosterone or give them, large amounts of androgens or steroids, we see large increases in muscle, we see large increases in strength. Now, the opposite or the caveat to that is now we're seeing similar things with estrogen, in that we might not see the huge changes in muscle mass, we're not seeing huge changes in muscle strength, but the contractile properties of the muscle are changing. There's no doubt about that. Or at least from our lab's perspective, we don't have a doubt about that from the findings that we have seen. If that plays out into humans, unsure at this point in time, but we're currently working on grants that will hopefully transition them from the mouse model to studying potentially males who are interested in transitioning to females and how that might impact their muscle function. This in the same way, the other way around of females interested in transitioning to males.
Yeah, from my understanding, there's also anatomical differences, right? It's not just the muscle function itself, anatomical differences that give biological males certain benefits for sports performance that can't be modified with just hormone treatment, right? But that's a completely different topic. What I really wanted to ask is how can we use all of this research to help inform and improve health related outcomes in the general population?
Yeah, and I think that's what most people are probably interested in, and that's honestly something I'm very much so interested in as well. And that I don't want to just understand how it works; I want to understand how you can make it better. And clearly, that's something that, like, if you look at the Olympics that are going on, it's like people are like, "Oh, how do we make this better?" And one of the main avenues is people obviously know is exercise. Exercise is probably going to make most any of these states a little bit better. Now the question is targeted approaches to exercise, and that's where my lab is really, a lab I work in is really interested in focusing on, is to say what types of exercise can we do after we have understood what's happening at the molecular level. What interventions can we do to improve that disease state? How can we improve physical function and improve ultimately quality of life? It's not just the physical function, it's the quality of life aspect. So if that means that the kinetics or the contractile velocities of single fibers are slowing, then we need to employ resistance exercise that's targeted to that. Now, this is where the sex differences come back into play, though, in that males and females may respond differently to the same program. And that's where the study that my lab's currently working on with the older adults and the resistance versus power training, that's where it came from, is that my advisor had individuals go through the same resistance training program for 16 weeks and they had different responses to it. So that's where we need to look at, potentially disease specific or sex specific interventions for exercise training. That could be cardiovascular, it could be, muscle strengthening. The other avenue, which hopefully will work in conjunction with this, and even is potential drug interventions. Now, you might think, well, how would you have a drug intervention that's for skeletal muscle? And that's a good question, because most people, that their first thought is just give them steroids. That may not always be solving the problem, because you have something that it works very systemically. You give someone a drug that works everywhere in their body. Yes, it works on muscle, but it also works on the heart. It also has impact to the kidneys. It also has impacts to the brain. It also has impacts to the cardiovascular system as a whole. So even though you might improve their physical function, you very well could be taking away from their other health metrics and making their quality of life worse. And this is something you can also think of, things like other things that have improved muscle function are things like, uh, another banned substance that people may know is clenbuterol. It's essentially an asthmatic medication, or a medication for people with asthma. It helps to increase the airflow to your lungs, but it also has receptors on that binds to your heart, and has receptors that binds to your muscle mass that make your heart beat faster and beat harder and make your muscles contract more forcefully. So there's other medications that also impact your muscles that might improve function, but they're going to have other detrimental properties. They might, cause you to go into cardiac arrest. That's clearly an exaggeration, but they're going to cause downstream effects that we may not want. So recently, and you can think of this as similar to some of the obesity medications that have been coming out, is we have more targeted drug interventions that may improve function of tissue. So you can think of the, Ozempic Wegovy. It targets some of the factors in your brain, or some of the receptors in your brain that say, be less hungry. Don't focus on food as much. We actually are now working, well, not my lab in particular, but we have experimented with some of these drugs, is in some of our mouse models, is that there are drugs that target single proteins. And essentially, they will bind to the myosin protein, or they will bind to one of the regulatory proteins of actin, and they will say either inhibit contraction, so stop it from happening, or they will say promote contraction, so promote these two molecules to work together. Now, the skeletal muscle side of things is a little bit uh, behind the cardiac tissue, behind the cardiac studies, or the heart studies, because people are very interested in, changing or impacting heart disease at this point in time, but it's slowly coming along the way. But what we have in the heart at the moment is there is one drug that has been approved for human use by the FDA, and that's mavacamten. I don't know the drug name, but that's the name that we use in the lab when we talk about this. And it essentially is a inhibitor of myosin function. So in the heart, what you see with people with heart failure, some individuals with heart failure, is the heart becomes very large and it becomes very, very strong. So what this drug does is it is attaches to the myosin molecule and says, do not bind as much, produce less force. So that will essentially make the heart work more like a normal heart. It produces less force, it doesn't contract as hard, and hopefully what will happen is the heart will start to become smaller. The other side of the coin is we also have a myosin activator, and it's essentially another molecule that will bind to act or bind to myosin and promote myosin binding to actin. What's cool about that is it does the exact opposite. It improves force production, it improves contractility of the heart, and then it improves heart function. So those are very targeted approaches to addressing heart disease. And in the near future, they're working on, some of these laboratories are working on specific modulators for skeletal muscle function as well. The hard part about that is that skeletal muscle and heart muscle have a lot of overlap between the receptors associated on the tissues, as well as how these drugs might impact both of them at the same time. So it's not always extremely specific. Some things are extremely specific, some things are not. And if they are not extremely specific, you might try and target something in the muscle and inadvertently start impacting your heart too, which is what we don't want, is why muscle's a little bit behind the cardiac world at this point in time. But that's kind of where this future is going, is we're going to have interventions that we can do as individuals. We can say, as practitioners, we can say, you should do these types of exercises, you should perform the exercises in a specific way. We should come at this with this type of nutritional intervention, whether it be, reduced calories, protein, or something of a sort. And then we can have the last arm of it really kicking it home, which is what specific drug interventions are going to help this population so that they can improve their muscle function and then improve their quality of life.
Yeah, man. Thank you for sharing all that. And I just wanted to touch on something because I feel like sometimes people get so lost in the weeds and focus on really hyper specific details when you talk about more specialized and targeted exercise interventions and nutritional interventions. Um, I'd love to get your take on this, and then we'll wrap this up. It's more specific interventions can improve the effectiveness of the modality that you're using, right? Whether it's exercise, nutrition, or whatnot. But general exercise and nutrition is still going to be across the board vastly beneficial for everyone.
Oh yeah, yeah. There's a the lion's share of the work is doing something.
Yeah.
It's like there's there's a bunch of work that came out looking at maybe not a bunch of work, but a decent amount of work showing that doing literally one set of an exercise is going to get you almost all of the way there. And then the next, 3, 4, or 5 sets are just kind of topping off the tank. And then when respect to strength gains, with respect to muscle mass gains, especially in untrained individuals who don't really do a whole lot. So if I had somebody coming to me who was like, if they had, some sort of metabolic disease, if they had diabetes, if they had kidney disease, if they had heart disease, if they are someone who is just overweight, looking, to lose some weight and feel better and look better, whatever it might be, my first thing is, what are you doing now? And if you're not doing anything, let's get you doing something that you enjoy doing. So it doesn't mean to say, from the researcher's perspective, I might say the best thing you could do is power training this many times per week for this long, but that negates all of the outside factors that influence our behavior as individuals. That's not taking into account the person has a job. They might not sleep as much as they want to. They might have kids. They might have other family that to take care of. They might have all these other responsibilities. So it boils down to, number one, what is most reasonable and realistic for you to do as an individual, depending upon your schedule. Number two is, what do you enjoy doing? And if you can match those two things up, and if you are doing something, whether it to be some sort of physical activity, whether it be some sort of diet that's going to help you slowly be going in the direction you want to go, those things are going to take care of the lion's share of the work. All the minutia that the lab that I work in is interested in is just improving on those things. It's making them more targeted so that you can go from, having a very high quality of life for the next 10 years to maybe the next 15. Maybe you feel good for the next 20 years. And you can improve or enjoy more time with your friends, family, and loved ones instead of, having some sort of disease that's really taking you away from enjoying your life and your time with other individuals. And that's where it really bridges the gap between, the research aspect, which is really hypothetical at times, into the clinical and, practitioner aspect of, what I like to do. And that, yes, all these details and intricacies are interesting to me and they're important, but boiling that down to, again, what is reasonable, realistic, and what people enjoy is going to be the biggest impact to their overall health and quality of life for the long term.
Yeah, thank you for sharing that, man. And thank you so much for taking time to come on the podcast and sharing your expertise with us.
Yeah.
Do you mind sharing where people can connect with you on social media?
Sure. So my primary avenue is Instagram. It's Doctor Mom. It's not very intuitive there because that's just my last name. But if you're interested in knowing how to pronounce it, the B is actually silent, so it's like you're talking to your mother.
That's too funny. And for those of you guys listening, the link to his social media profile will be down in the description as well. Definitely go ahead and give Brent a follow. Brent's getting active on social media now, and he's been posting some great content on there, some really practical advice to help you improve health, build muscle, improve body composition, all the great stuff that I tend to talk about on social media as well. For those of you guys that listened to the entire episode, I hope you enjoyed it. As always, if you're a regular listener, all I ask is that you take a second to rate the podcast and leave a review. It helps me a ton, and I would really, really appreciate it. Hope you enjoyed the episode, and I'll catch you in next week's episode. See ya.